Alright, this is the video that I am posting as like my assignment along with all the images for learning module 2 here for my computer design here. Because of course I could just like give you the images, but that won't really be helpful because there's probably like 2 million mistakes in here. So I'm gonna kind of narrate along all these pages that I drew, all these diagrams I drew to make it a little bit more clear as to what's going on in this image, because obviously this isn't a program, this is a drawing, and graphite on paper does not equal a compiled text document. So I'm going to work backwards here from this main page, which is the entire computer design. You could describe it as the CPU, but it's the entire computer, so I don't really know if CPU is an applicable term here. But we'll kind of just work backwards from this, because you'll notice most of this is not logic gates. I mean, there are some like here and here, but most of these are just blocks with lines sticking out of them. So we're going to work backwards from all these abstractions. So the largest component of this, and frankly the most important one, is going to be the RAM, the random access memory. So I'll pull out my diagram for that. So in here, similarly before, this also has a lot of abstractions. So in this case, you can see we have these wires here. So and these correspond to this block right here. So in this case, these eight inputs here are equal to these 8 inputs up here, and these 10 inputs here are equal to these 10 here, and these 10 outputs are equal to these 10 output wires, and this write enable inputs is equal to this wire here. But can't just get started on this because there's a lot of abstractions. So I'll move down a step. There's only one abstraction, well, kind of 2 abstractions. But in this case, we'll go back to the more important one, which is this here, the 10-bit register. So grab our drawing here. This here is an 8-bit register. This pattern here can basically be expanded for as many bits as you want. This case it's 8 bits, because when I drew this, I didn't know if I need 10 or 8. But you'll notice corresponding here is with these, the 8 expanded to 10. But in this case, the 8 outputs here are the outputs over here. These inputs are equivalent to these inputs, and this write enable is equal to this line here. But this also has a lot of abstractions. In fact, this one doesn't contain any logic gates whatsoever. So we'll go back a level, back upon these L blocks, which is the latch. Now, let me preface, I did not design the latch. I think that's kind of obvious. This comes from the All Overlord Wikipedia. This is a very old design. There's no reason for me really to design something like this, because it works perfectly fine. It's basically what everybody else uses. It doesn't really negate the rest of the design, because if I design my own, it would have the same functionality as this anyways. So in this here, we have our write enable, our input, what does that say? Our data input, and our output here. So, and assuming you don't know what a latch is, in this case, the output is equal, well, this is different than most logic gates because it's dependent on what the last, what happened last time you activated this. So assuming everything in here is deactivated, so these inputs are 0 and 0. If the write enable is 1, then this output is equal to whatever the data line is. So if this is 1 and this is 1, this will be 1. If this is 1 and this is 0, this will be 0. But if you set the write enable to 0, it will freeze whatever the data line is over here. So if this is 1, this is 1, this will be 1 here. And if we suddenly turn this to 0, this will stay as 1, and no matter if we turn this to 1 or 0, it will stay as 1. And it won't change until we set the write enable to 1. And some abstraction, abstracted to this block here. We have 2 outputs, top being write enable, bottom being the data line, and this being output. So we go over here. We have our data lines here, our write enable up here, our blocks here, and the outputs here. So this is basically an expanded version of this, but instead of having one data input, it has multiple data inputs and multiple data outputs. So in this case, we're basically putting a bunch of these next to each other in series, and then connecting all the write enables to the same input. That's basically what this is here. And we abstract this here. I abstracted it to a capital B because it's a byte, 8 bits. But of course, this can be any number greater than, well, it could be any number greater than or equal to 1. You know, any integer greater or equal than 1. So we go back to our RAM design here. You'll notice we have this 10-bit register, which you can explain later why it would be 10 bits. I believe 10 bits would be called like a decabit or something. I'm not sure. It's 1 byte plus 2 extra bits. It's basically what it is. So in this case, we start off here with our input lines. There's 10 of them, and our 10 output lines. The write enable, and this up here is our address. So basically, in the block that we set to be in our RAM module here, what we set the address to be will be our address in RAM. So it could be any 8-bit number. So it could be anywhere from 0 to 255. And anywhere from 0 to 255. And that address will be accessed from this. Imagine there's only two, yeah, I should start back over again. There's only 2 registers here, all right? But there's 256 addresses, which means there's 256 of these 10-bit locations in our RAM. So basically, imagine I don't have a piece of paper that's big enough to draw 256 of these, all right? This continues forever. So in this case, you'll notice in our demultiplexer, it's opposite of a multiplexer. So you give it a number, it'll give you a wire. I'll go over demultiplexers a little bit later. But in this case, it's an 8-bit demultiplexer, so wire 1 goes straight from alright, so basically let's just look at one of these registers. Alright, so every register is like this. They're all identical to this module here, except for this pencil here. Except for this line right here. This is the only thing that is different. In this case, each of these will be connected up to the demultiplexer, equal to their position. So in this case, this is the first position, or the 0th position. So it's connected to the 0th position of the demultiplexer. This is the second one, so it's connected to the second position, and that goes on and on until 256, when there's no more locations on a demultiplexer. In this case, our right enable line is ANDed, and presume that. I perfectly assume you know what that means. So when the right enable is ANDed with the signal from our demultiplexer, which means that the output of this is equal to 1 when and only when our demultiplexer's address is the binary number equal to this address. All right, and when that happens, our right enable for this register is enabled, of course, and if you remember, that means that we are replacing all of the registers that are in here. We're setting their data lines, and their data lines are equal to these here, which you'll notice are equal to our 10. They're equal to our 10 inputs, our 10 inputs, 10 input lines here, which you'll remember from over here. So, they go straight into our 10 input lines, and every single register has these same inputs. These same 10 inputs here are equal to these lines here, but they don't mean anything, because remember, the register will not consider these inputs at all unless the right enable is on, and the right enable is only on when both the RAM's right enable is on and when their address is activated, which in this case means that that register is rewritten when that's the case to whatever these are set to. All right. Now, of course, there's a second function to RAMs, which is not only writing, but you have to read too. You know, it's access memory, not write-only memory or read-only memory. We have to read and write. So in this case, we want to read the register associated with the address when we give it that address. So in this case, if we wanted to read, like 1, RAM position 1, we'd have to set this these outputs to the binary number 1. And for any other inputs there, and the output will be equal to that to the register that we're accessing. And you might wonder why, because we have 256 times 10, so it's like 2,000 wires going straight into here. It will all be confusing because it basically just maxed out to 1 or 0. Practically would just be 256, not 256, 1024 would be the output here if that's the case, which is why we need these sets of AND gates. That way, when this address is activated, it will go straight. When it's activated, it'll go straight into these, allowing the contents of this to move forward and be integrated into the output. In this case, there's a bit of a mistake over here where, of course, there's no nil value for logic gates. It's either 0 or 1. So in this case, I'm basically, all these wires are going to have like 0, 0, 0, 0, like 256 zeros, and maybe 1, 1, or maybe it's all zeros. And that's confusing because you can't have multiple inputs. So in that case, I can't really draw this here. It just doesn't work. These wires here are their max, the largest value that they're given, which just means it's their OR. So these wires are equal to the OR of their inputs here. And I believe there's a little mistake, not a little mistake, it's kind of a big mistake that I didn't notice because I haven't touched this paper in a while. So let me fix that. These AND positions would only be enabled when the right enable's on. That's not correct. We want this to be, let's just fix this here. So this is a little old. I can't really erase this well. So the input here is now the register thing here. Sorry, probably should have noticed that a while ago, but I didn't. And that's gonna happen a lot as I go through these papers, as some of them are a little old and they all have mistakes because I can't really test this very well. So it should be explanation for the RAM. So let's come back to see what else we have here. So basically everything on here has been explained except for the clock and a 2-bit demultiplexer and these little things here that say T on them. So let's go over those two. Let's start with the little T blocks. So this was recent. I did not expect to make this until like a couple days ago, and then it occurred to me it was really obvious I needed this. So here we go. This is, ignore all this. This is how I extrapolated. Maybe that's not the right term. This is how I found out how to make this circuit. This is the truth table. So in this case, this is what I'm calling a picker to choose between two values. So in this case, the output, this output here is equal to, I mean, you can follow this if you want, follow these gates if you want, or just listen to my mumbling here. So when the toggle in is equal to 0, the output will be equal to the first input 0. If toggle is equal to 1, the output will be equal to 1. That's basically it. But to make it easier for me to draw a bunch of these, I did take the toggle input and straight to an output. That way I could draw it as this. So you have so in this case you can stack them. So you'll see over here, the top, this whole chain here there's 8 of these T blocks, and all of them have their two things, like this is 0, this is 1, this is 0, 1, 0, 1, you know, and they have this one toggle here. And this toggle, you can imagine, goes through here, it outputs out of this, and it stays the exact same as this. You can almost imagine like this is just running right besides it and going into all of them, and they're all the same. But for my ease, I basically made it so they could chain together by making the input, this input here is equal to the output here, and just stacking them on top of each other, like I don't know, Legos, I guess. All right, that are the pickers. Let's see, there's 2 more. Let's go over the adder. The adder is not particularly interesting because I did not design this either. This also comes from Wikipedia. Let me grab it. So I'm gonna explain anyways. Let's see. So the functionality of the adder basically takes two 8-bit numbers and outputs an 8-bit number that's equal to their sum. It kind of is self-explanatory. So, in this case, this is the full adder. It's not really, you can't really see all of that once it's here. So these 8 are our first input, our first byte, and these are our second byte, and they go through this like web of full adders to give us the sum. And it kind of looks like this. I basically, it can look like this. I basically just said whatever, as long as I define where my inputs and outputs, I think it's okay. I mean, not professionally, but I mean, like, basically, like, in practice, it's probably okay. Because, when you have two chunks of input and one chunk of output, that's kind of hard to draw, because then you have just one unused side. But anyways, these full adders here are this is what I got from Wikipedia. All right, so a full adder will basically give you the sum of these 3 numbers, and these are 1-bit numbers, so, you know, you're basically just like adding 1 plus 1 plus 1, or 1 plus 0 plus 0, or, you know, whatever. It's the sum of these 3 numbers, which outputs its sum, and if its sum is greater than 1, you give you an output. You give you carry. And basically what you can do with that is, when you go back to start here, it starts with the sum of this number and this number. And if that number is greater than 1, this carry goes in here and it sums these 3 together. Same process. It sums all these together to get you the full number. Because, you know, if you didn't use the carry here, you'd get well, it wouldn't really be adding. I guess it'd be like I don't know, kind of just like, what would it be? I guess a bunch of like XOR gates. These would basically be XOR gates if you didn't, exclusive OR gates if you didn't use the carry line. Like I said, this came from Wikipedia. I didn't design this myself because it take like 5 weeks to design this thing here. This is the system like everybody uses, you know. There's no reason to fix something if it ain't broke. So, last part, and I promise that's the last of the things that came from Wikipedia. The rest of these I designed myself, including the architecture. I mean, the only 2 things I only took 2 things from Wikipedia: the adder and the latch. Everything else I designed myself. Just make sure that's clear. So let's go on to the last part, and that is the clock. So the clock outputs it has no inputs, but it has 2 outputs. All right. So this is kind of different than the rest of them because, you know, this is like a temporal dimension or whatever. All right, so you have we have our clock, our square wave clock. So basically, what a square wave clock is basically it goes a square wave clock as time, it consistently gives you 0 1 0 1 0 1 0 1 0 1 0 1 0 at a consistent frequency. So like in real life this would be like a 555 timer, or maybe in real life it could also be like the AC current if you wanted a really slow computer. In this case it's just high low high low high low, and I don't want high low high low high low. I don't want that because of I have 4 commands in this CPU design, so I want it to go, and these commands are a little bit more complicated. All right, maybe I shouldn't. Okay, wrong way to word it. All right, so one of these 4 commands here needs 3 clock cycles. In this case, we only have 2 clock cycles, which is just high, low, high, low. So in this case, what we're going to do is we're going to do there's a term for this. What's it called? Frequency divider, right? So a frequency divider in this case is just a latch, which we saw earlier, but you take the inverse of its output and feed that back into the right enable. All right. And basically what it does is imagine this is our final clock here. So imagine we go, this is our clock. So as time goes on, it's low, high, low, high, low, high, low, high, etc. And what a pulse divider does is every time that the clock goes high, low, it will kind of count on its own. It basically, a pulse divider is taking your frequency and dividing it by 2. That's basically what it's doing, all right? So in this case, we divided it from 2 inputs, so it's high, low, into 4, which is low would be 0, 0, 0, 1, 1, 0, 1, 1, 1, all right? So that's 4. In this case, they go up incrementally. So it starts at 0, 0, 0, and then as time moves on, the main pulse will go down, other way. The main pulse starts at 0, and then it will go, which sets it as our main clock as 0, 0. And then as time marches along, it will go high. Our main clock goes high. And when it does that, we now have 0, 1. So after that, as time moves on along again, it'd go back down to 0. But remember, we have this pulse divider here. So you can imagine we just multiplied it by 2. We basically added 2. So kind of imagine, like, if this is our main clock here, we're basically adding 2 at half this frequency. So it goes up, down, up, down. But in this case, this activates it. So now we add 2. So it goes down, up, up, and then it gets reset back to 0. It goes on and on. It makes it, I'm not good at explaining this. All right, this creates, oops, that is upside down. This creates a sawtooth, something that resembles a sawtooth wave. And if this was like a much more complicated CPU, we could just like use a sine wave generator, like the ones you can buy as circuits. But in this case, these are discrete values because we're working with all these discrete things here. This is not, we don't need that kind of fine control. So basically it's a long way of saying this outputs a 2-bit number that goes up and then straight back down, up, down, goes up, down, up, down, up, down. That's basically what it's doing, which we could use by itself. There's nothing wrong with that because I can just derive that from itself. But for ease, we put that into a duplexer. So basically we give it our number here, in this case it's 2-bit, and it outputs all the possible, the number of outputs will be equal to the number of possible outputs there could be. So in this case it's 4, because the largest number you can get with 2 bits is 4. So in this case, if we have 0, 0 as our inputs, it will not be true anywhere except down here. All right, and if it's 0, 1, it'll only be true up here and nowhere else, and that pattern continues until it goes back to 0, 0, and it goes up and down. Basically, it gives us these 4 signals here, which tells us if the clock is equal, if the clock is equal to a certain value. And actually I use this duplexer in another way because remember before I said this prematurely, we have 4 commands here. So I wrote these down. These are the 4 commands of the CPU. I don't know how well you can read this, not just because of the bad handwriting, but the lighting's a bit weird. I think if I zoom in, I'll look a bit better. So in this case, we have 4 here, and these correspond to a 2-bit number, because there's 4. You can represent 4 things with 2 bits, and that comes back to why did the RAM have 10-bit inputs? And that's because each RAM address starts with 2 bits and then 8 bits. The first 2 bits are equal to its command, the command that it is running when that thing is accessed, when that address is accessed. And then the next 8 bits are, the number it actually wants us to compute with it. And because I wanted there to be 256 memory addresses, I had to make it so the largest number that you could given these largest number given the commands I made, the commands I designed, you need to be able to tell it that you want to go anywhere between 0 and 256, or 0 and 255, and that means you have to have 1 byte of information to tell it what the address is. All right, so let's go back and just give these and just describe all these commands here. So command 00 is to tell our position register, which we'll cover later, to go to this is all like off the cuff, okay? So I'm just saying a lot of things here that don't make sense. So imagine, like in a normal programming language, you basically have like a pointer that executes each line, and sometimes they'll jump up and down depending on the language, because in this case it's assembly or machine language. So basically, in this case, in this machine language, which is basically just a masochistic programming language, in machine language, you have your position counter, and that just goes through the entire RAM, and whatever it's told, this is a little difficult to explain here. So, so basically, we access a RAM address. So RAM, it has an address here, and we need to set this address to be something. So in this case, when the program first starts, when the computer is first booted up, it will be 00000. All right, it's 1 byte of 0, and in that case, it will every CPU cycle. So every time we cycle through one of these, it will go up 1. All right, it'll go up 1. All right, and the exception is if we tell it to execute command 00. If we tell it to execute command 00, it will set the position register to be equal to whatever we have in our main register. All right, and our main register is kind of just like the area we set aside to do calculations, which has you obviously know. I just I had to say that. So and then our next command here is 01, which is to set register to value in position. So that basically means the main register we have the main register, which we have up here, is set to a value within the RAM. All right. So, second. Okay. So basically it sets the register to a value in RAM given the address. So if we say the command is 01 and then I don't know, something like 56, 0156, and then I guess it's 1 followed by 56. That would mean that our register up here has been set to whatever value is stored in RAM at value 56. All right. Next command here is 10, which is the opposite. So in this case, given the address that we set, it will set the value in RAM to whatever is in the register. So in this case, you know, if it's executing command 2 followed by 56, then that means that the 56th position in our RAM will be equal to whatever the register is. All right. And then lastly is command 11. This is the oddball of the group here. We have to, in this case, in command 11, you add whatever number is in the register here is added, which we covered the full adder before, is added with whatever you told it to do. So in this case, if it was executing command 3 followed by 56, that means that the register is now equal to whatever value it was plus 56. All right, and those are all 4 commands. And now I think that's enough to cover maybe at least some of what we're looking at here. So the design process for, I'll set this in front of you while I look for the papers. The design process basically started with me creating a CPU design for each of the 4 commands and then combining them all into one CPU design. So if I can pull them out here, I have, this is command 00, command 3, command 2, and I believe, no, that's not it. Latch. Command 1 should be somewhere around here. There's a lot of papers here, so I'm kind of scraping through all of them. It should be right around here. I cannot find command 1, but that shouldn't be a big deal because I have a CPU design that should be a combination of 0 and 1, I think. Let's see. I think, because I kind of just forget these, so I don't want to remember these useless pieces of paper. I keep them anyways, because you might as well. No, I think it should be around here. Maybe is it under here? So I know so this is 1, 3, 0. Where is 1? I guess we're just gonna ignore command 1 for now, which is not a big deal because it's not abstraction. This is just, I'm just showing the design process here. So, in this case, move these over. So we can start with, say, let's start with 3. So if you remember 3 or 1, 1 is the command which adds a number to the register. So in this case, when the clock is equal to 0, command is set. So we set the command register to whatever is in the output. And if the first 2 are equal to 1 and 1, then if they're equal to 1, 1, and the clock is on cycle 4, then that means that the register is write enable. All right, so we can set anything to the register. In this case, the register is equal to these lines here, and these lines here are equal to command plus the command output plus the register output. So basically, we're rewriting the register to be equal to it plus whatever is in the command. All right. This case can go down here. This is command 0, 0. This is one of the more complicated ones. So let's skip over this one. And this is 1, 1, 0. This is command 2. So in this case, just like before, on cycle 0, we set this command. We set it in stone for the rest of the cycle to whatever is an address up here. And if the command is equal to 1, 0, then write enable is turned on. Well, if this is on, and if we're on cycle 3 out of 4, then write enable is on. And now we can input, our input can now be, we can write to RAM address up here as register. Now the RAM address up here is equal to command because when this is the case, we have changed it from being position and chosen to take the RAM position here, the command position here. So now it's rewritten, when this happens, it's rewritten the, wherever this position is here as this value in this location, All right, now, in 0, 0, which is this is the more complicated one. This is basically the counter. This is how the position works. In this case, like before, we input this here, and if the command here is equal to 0, 0, then all right, it's a little difficult to explain. So we have this little thing down here, all right? And basically what this thing does is it will, okay, it's a little difficult. So I have a truth table up here, all right? If this is more useful, this is the truth table for it. So basically what it's saying is basically what it's doing is that when these two are equal to, basically it's saying that, it's basically saying that if the command is equal to this, if the input 1 here is equal to, if the input is 1 and this is 0, and just look at the truth table. I'm getting tired. All right, so in this case, basically what it's doing is saying that in this case, what it's doing is basically saying the position register here is equal to position plus 1. So now we're just going down by 1. It's equal to position plus 1 if the command is not equal to 0, 0. But if it is equal to 0, 0, then they will set the write enable on the choose when so that it writes this as the position in register. And then so as it continues, it's now its new starting point for going on and on. Yeah, what's the one I was missing is 1. And 1 should be set register to a value and position. That one's simple. Basically just say set register equal to the RAM, and the RAM address is equal to whatever the command was. So, and now basically when we combine all 4 of these together, they combine all together into this giant thing. This thing probably has mistakes because I don't really have a way to test this. And I made this earlier today, so it's not that thorough, but I'm going to go over a pre-written program I have to test this out to show how this works. And hopefully then, if there's a kink in here, I'll find it, alright? So, in the second video, I'm going to just run over a program that I wrote. That I wrote to basically run through this entire thing. I forgot to explain one more thing. When we set in command 2, which if you remember, command 2 is to set a value in our RAM equal to the value in the register at position in command. In that case, I actually made this decision to, because the command gives us a 1-bit output, that doesn't give us the option to rewrite all 10 bits, which is definitely a flaw on my part, that I probably should have thought of earlier, but which means that you can't rewrite the command in that position. You can only rewrite the last 8 bits. And I was not satisfied with that, so I set it so that, I think you should see it here, the first 2 bits are equal to the last 2 bits of the register, which basically means, which is not easy for the programmer, by the way, but in this case, it should mean that you can rewrite the command if you want to, which, makes this, much more conducive to things like operating systems. If for some reason I decide to do that, it would make it more conducive to things like operating systems and the like, because then it lets you rewrite a program. And while it's not easy for the programmer, it would be possible, because before it just wouldn't be possible at all. All right, I think that should be it. I believe all these pages will be put in the School G thing or whatever it's assigned to, that when I turn it in. If it's not, then it's in this video. All right, I think that's it. This is very long. I'm not offended if you did not watch this entire thing. All right, I think that's it.